Well, hello everyone, welcome to Sabancı University. So my name is Serkant. For those who don't know me, I'm an assistant professor of political science at Sabancı. So today I'll be talking about causal inference with observational data. And in particular, our focus is going to be on DID, difference in difference strategy. But before coming to DID, there are some things that we need to cover. And hopefully, if we have time, I'm going to also show you another design, which is called Regression Discontinuity Design. And then we'll do an application using print media data, a small application. It's going to be a little dirty, and you'll see why that's dirty. So that's, well, I have 100 slides, so bear with me today. Hopefully, I'm going to be, I'm going to be also try to be quick, but I don't want to also miss things. So feel free to interrupt me anytime you want, all right? So, causality, causal effects, and the counterfactual. So, causality. So, by the way, has anyone? This is just to first. I'm going to be using a lot of material from Koskei's textbook. So, this is an excellent textbook that also has lots of application in it. And this is the Thai-diverse version. So, I think you already know R by now. So, it uses the Thai-diverse language within R. So, it's a nice textbook. And the library is QSS. That's the library that the data is going to come from that library because it's already clean and ready to use. All right. So, has anyone taken causal inference class before? You don't count, Hocam. Well, there are some. Okay. So, causality is one of the most central concepts in quantitative social science, right? So, most of the time we ask questions about like whether X causes Y, right? For instance, does democracy cause economic growth? That's a very important question, but it's also very difficult to answer, right, in a causal setting. The reason is because we need to always infer the counterfactual outcome, right? So what is the counterfactual? Assume that, for instance, the United States is a democracy, right? And also there's like years of economic growth in the US. Whether democracy is causing economic growth, in order to answer that, we need to have this counterfactual United States, where United States was not democracy. And you can tell that the United States is not a perfect democracy, but assuming a counterfactual where United States is an autocracy, right? And then United States is a democracy today, then we need to compare those two cases in order to really understand whether democracy is causing economic growth or not. Well, what's the problem? Well, the problem is we don't observe that counterfactual, right? We don't observe a fully autocratic United States. So that's the main problem of causal inference. The fundamental problem of causal inference is that, well, we need to know the counterfactual, but the counterfactual is not observed, right? Then what are we going to do? Well, we need a credible way to infer the counterfactual from the observed data. So how are we going to do that? Well, the gold standard is experiments. So in experimental setting, what you do is you randomly divide, right, the basic experimental research design. You randomly divide your sample into two, right? Let's say you are interested in knowing whether Summer Institute in Computational Social Science will get you a data science job. What we can do here is we can just divide this sample into two, right? This half can get the training, and this half will not get the training. And if you randomize this treatment, in this case, it's computational social science education, then you can observe the outcomes after a while, right? So then you can observe your employment outcomes. And experimental setting, you will solve this fundamental problem of causal inference. Why? Because if you randomly assign this treatment, which is the training, the groups are going to be comparable, right? Because we are randomizing it. Randomization ensures that treatment and control groups are comparable, except for one thing, which is the treatment assignment, right? Since those two groups are comparable, randomization makes sure that we can compare these two things, and control group is going to be the group where we infer the counterfactual for the treatment, right? So this is actually the gold standard in establishing causality, which actually gave also, so for instance, I think the last Nobel Prize went to RCTs, right? So the RCT people, Duflo and but the problem is, of course, causal inference is essentially comparing these two things, the counterfactual and also the factual. Well, the problem is you cannot randomize everything. But for instance, the democracy example I gave you, right? You cannot randomly assign democracy to countries and then compare their economic growth. So first, a little bit of notation, just to make sure that like we're on the same page. So most of the time, if you ever taken a causal inference class, you'll see this potential outcomes framework. So the problem here is the causal effect is essentially the difference between these two things. So the potential outcome in the presence of treatment for individual I minus potential outcome in the absence of treatment. Going back to our example, computational social science training. So this would be your employment outcome if you get the training. In this case, you are all getting it, right? And this would be the counterfactual, which we don't observe for any of you, right? Because you are getting the training. So there is this counterfactual of you in this parallel universe that we need to infer somehow, right? And that's why I zero. But the problem is, as I told you, we only observe one or the other, which is the fundamental problem of causal inference. So that's why we need to infer this. But of course, in order to infer that, we need to make some assumptions. And this is what we mean by identification assumptions. So if you read or if you attend an academic lecture in these days, right, in social science, like in econ or political science, you will see at some point the presenter is going to talk about identification assumptions. So identification assumption is essentially identifying the causal impact. So there is this assumption required to make that causal claim. So that's called identification assumption. And well, randomization. So that's the gold standard where you can actually infer the counterfactual. But of course, as I told you, randomization sometimes is not practical. Sometimes it's not difficult. So what are we going to do? Because there are lots of data, right? It's like, for instance, social media data, media data, survey data, where you don't have any control in data generating process. So what it means is that you're just observing the things naturally. You take that, right? So unlike RCTs where so by the way, by RCT, I mean randomized control trials. Unlike experimental setting, you don't have any control. So that means you're just recording, you're just observing, hence the name observational data. All right. So in this case, of course, internal validity, what we call internal validity, is more likely to be compromised, meaning that you cannot simply compare control and treatment groups. Why? Because people or units are going to self-select themselves into groups. So, for instance, United States is democracy, not just out of sheer blood or some, a God-divine randomization assignment or something like that, right? US is democracy for whatever reasons. So that's why internal validity is more likely to be compromised in observational setting. Though the external validity, which means the generalized, so the results can be more generalizable, unlike us. So there's a whole discussion about these things, and if you want to know more, I can direct you some readings. But the problem in observation setting is that we simply have no control in data generating process. If you ever, so I mean, I'm sure you're going to take a causal inference class in your future life. You'll start, well, if you ever cover DID, you will probably start with this famous paper, Carter and Kruger minimum wage example, so published in American Economic Review in 1994. So the question here is, what happens when there's an increase in minimum wage? So if you ever take an Econ 101, right, supply and demand, so that's very simplistic answer is going to be, oh, if you increase minimum wage, then unemployment will rise, right? But if you look at empirical studies, there is no evidence. So this is actually 101. Actually, I think this is the one, like the first paper that tries to answer this in a credible manner. So what they do is they examine the impact of raising the minimum wage on employment in fast food industry. So why fast food? Well, it's a standard, right? So the products are comparable. That's why there's this Big Mac index, right? So the products are pretty standard. That's why you can compare across different settings. So what happened is in 1992, New Jersey raised the minimum wage from $4.25 to $5.05 per hour. So in order to answer whether minimum wage increase, the impact of minimum wage increase on employment, we need to have this counterfactual New Jersey, right, in this parallel universe where this minimum wage increase didn't happen. Well, what's the problem? There's no such New Jersey, right? How are we gonna find this New Jersey? So what they do is they infer this by looking at a similar state. Since New Jersey, counterfactual New Jersey is not observable. So what they do is they use Pennsylvania, which is the neighboring state, and they actually chose counties closer to New Jersey border, and they compare fast food restaurants in these two states. So this is the setting. All right. The claim is, of course, Pennsylvania is comparable to New Jersey. The nice thing is that you can actually, if you have data, you can kind of test this, which I'll briefly explain as well. First, let's start with very simple design. So I'm going to show you two simple designs, and then we'll combine them, where we're going to have differences once we combine them. So first, what we're going to do is we're just going to compare New Jersey and Pennsylvania, and the outcome is full-time employees. All right. So that's what we're going to be using. So you can code with me as you go. So QSS is the library where this minimum wage data comes, and I'm still using the old pipe in R. So well, now there is a base R piping. So this is a Madrid's pipe, but there's also base piping now. By piping, I think you now know what I mean, right? So this is one way of writing the code. So once you load the data, it's always a good practice just to inspect what you load, right? So this is the data. So first 6 rows. These are essentially the restaurants, fast food restaurants. All right. Wendy's, Burger, KFC, and the location states. So we have 2 states, New Jersey and Pennsylvania. And then wage before, wage after. So this is in wide structure. It's not in long format. So it's in wide format. All right. So this is the data set. I think is it. Does everyone now have it, or you are? Yeah. So once you load the data, do these usual checks. Any question? Yes. So if this doesn't work, data mean wage, you might not. You can declare the source. I think if you just do comma and then source something, there's an option should tell R that this is coming from QSS. Just do question mark data. You'll see the options in help section as well. Well, this is gonna be. I can send these slides as well, so you can always go back and work. And this is again from Imai's text.
Is there like a free online version of Imai's textbook, or like a book down? No.
Well, no.
Okay.
Yes.
I asked for like an inspection copy. They did.
Okay, let's talk after. But there's not. Yeah, the answer is I think there's the instructor's copy they might provide, but the copy I got is my parents sent it from the US because I was not. Now we have it in our bookstore, which is closer to dining hall. And this is this is not the most basic one, by the way. This is there's also one for undergrad specifically. Anyway, so I'm moving on. So just some functions I just threw here in case you probably already know this, right? Summary is just a summary of the data set. There's also a glimpse. I think this is from a high-diverse version of summary, I suppose. So all these things that are helpful when you load the data just to inspect everything is okay. So first thing, of course, did restaurants comply with the law, right? So this is it. So since we are interested in minimum wage increase, first we need to see whether they comply, right? Whether they take this treatment assignment. So this is the problem with observational data. If this were an experimental setting, we would simply randomize minimum wage increase to half of the restaurants, and assuming that they had to comply, right? It would make things easier. But in observational settings, sometimes there are the non-compliers. That's also the case in experimental setting, but we need to make sure that treatment is actually taken by these units. So by the way, so the location is just where these restaurants are located. So I'm just combining, so I'm just creating the state variable. So I'm just combining New Jersey's into one, all right? So now that I have this state variable, so I'm just grouping by state and then looking at the share of restaurants that comply with the law before and after. So just look at here, New Jersey, in like almost 100% of restaurants in New Jersey now offering more than 505, while in Pennsylvania, almost nothing, like it's 5% of restaurants are offering, because why? In Pennsylvania, there is no this is not the law, right? So it is clear that New Jersey restaurants comply with the law, so this is fine. So now at least now we can actually compare them. So as I told you, the outcome is proportional full-time workers. So first, as I told you, I'm going to do a simple thing where I'm going to compare New Jersey and Pennsylvania after this minimum wage increase. So this is cross-section comparison and only focusing on after the minimum wage increase. So, and I'll just use difference in means estimator, but you can also do it with OLS, right? So it's gonna give you the same result as well. So what do I do here? So first, I'm just so if you go back to the data, so there's a full and then there is parts, so part-time and full-time employment. So since I'm interested in full-time proportion, so what do I do is I'm just creating these full prop after, which is the full proportion. So this is just the share of full-time employments. All right, and this is the result. Full prop after. If you just like inspect the data, so this is the column I add with the mutate. So mutate you already know, right? So this is from the flyer. So you just create another column called full prop after. All right. Once you do that, you can simply look at what happened in terms of differences across New Jersey and Pennsylvania. This is after the minimum wage increase in New Jersey. So this is just cross-sectional comparison, where I'm just comparing New Jersey and Pennsylvania after the minimum wage increase in New Jersey, and the difference is 4.8, which shows that in New Jersey, full-time employment was around 5% higher compared to Pennsylvania. All right? Well, does this mean that minimum wage actually caused this increase? And this is a question for you. So I simply compare, right, after, let's say, so minimum wage increase happened in 1992. Let's assume this is 1994 data. So I simply compare the average full-time employment in Pennsylvania and New Jersey in 1994. So a difference in means. So, and then I found that it's around 5%. Do you believe that this is because of minimum wage, but nothing else? No, right? Why? Because, well, there are millions of other factors that could explain the difference between these two states, right? Simple comparison is not enough to conclude that it's because minimum wage. How do you know? Maybe there is, I don't know, there is another labor-intensive industry in New Jersey that is actually pushing, right? That is actually increasing wages in New Jersey. Maybe it's that, not the minimum wage. So you never know. So that's why we need to like consider all these other factors that might explain this difference. And this is actually confounding bias. So that's confounding bias, meaning that these unobserved factors that could have explained the difference is, if you omit them, then actually there is this confounding bias. Why confounding? Because it confounds the relationship that we are interested in. We are interested in minimum wage and employment. That causal relationship is confounded by factors that we exclude, right? We don't observe. So that's confounding bias. So what is actually, so there is no problem in experimental research. Why? Because since we are randomizing the treatment, on average, treatment and control groups are similar. What does it mean on average? So on average, of course, if you just like focus on individual units in groups, they're gonna be different. But if you take the average, let's say we randomize treatment assignment. So we randomize summer institute, and sample is just you, right? If you randomize it properly, let's say proportion of females, proportion of like I don't know, education, age, and all these things on average are going to be similar. But this might not be the case in observational data, right? Like units can self-select themselves into treatment assignment. And this is the example that I just gave you. So imagine in New Jersey there is this textile industry, right? And well, the argument is textile industry is more low-skilled labor intensive, all right? Which also in a fast food restaurant, the most of the employment is also low-skilled. So then in New Jersey there's going to be a competition for low-skilled labor, which then impact the outcome, the very outcome that we are interested in. So that's why this textile industry, if we just omit this, this is going to confound the relationship. The difference we see could be attributed to textile industry, right? While we don't observe this, if we just don't take that into account, then we will, well, it's going to bias our results, all right? So that means we cannot infer the counterfactual outcome from PA restaurants because they are not going to be comparable because of this confounding bias. So essentially, what confounding bias is any difference that explains the outcome other than the minimum wage increase is gonna be confounding relationship. And you can come up with other confounding variables as well, right? I don't know. Can you give an example, for instance? Like anything, right? Like anything that might impact. So by the way, I'm just gonna visualize the relationship here. The ggdat is the library I'm using here. You don't have to do like, okay, I'm just gonna add the, so here, so you'll see these graphs a lot if you're like studying causal inference. So what we are interested in this, right? So we are interested in the impact of W on employment. So impact of wages on employment. So we are interested in this causal direction, right? But imagine there is this L, which is labor, so textile industry. Imagine that L, which we don't take into account, while this L is impacting both E and W, right? So L impacts E, so low-skilled labor competition can impact full-time employment, right? But it also impacts minimum wage. So such L's, so in this case it's low-skilled labor competition, but any pre-treatment variables, so pre-treatment meaning that they are not impacted by the treatment itself, any pre-treatment variables that are associated with both the treatment and the outcome are known as confounders. Yes?
Should this confound variable has effect on both?
Yes. See the arrows? L is impacting both E and W. So any such variables that you can come up with in this particular setting, they're going to be known as confounders, all right? And if you just don't take them into account, then you cannot make this causal claim because this is omitted, all right? So in this particular case, low-skilled labor competition is the confounder. Yes, I did.
So confound variables cause problems, right?
Yes.
Okay. And I want to say that if there is confound variable, take false of let's say the example of Pennsylvania and New Jersey, should affect false of them not be.
Well, in this case, so the example is just, let's assume it's because of the labor, like low-skilled labor competition in New Jersey. That means the competition is different. So that means yes, any difference you observe in outcome can be attributed not to minimum wage increase, but low-skilled labor competition. But the problem is, of course, like you can come up with other possible differences across these two states, right? And I'm just giving one example. So, and this is critical because this will determine, right? This labor competition might impact who is likely to receive treatment. And this is actually, for instance, let's assume since there is this like labor competition, maybe states like this, politicians in New Jersey, they start demanding more, they start demanding increases in wages because of, maybe because of this competition. And that might actually impact why New Jersey adopted minimum wage increase in 1992. Maybe there is something specific to New Jersey. And in this example, it's labor competition, right? So then it is actually a selection bias. New Jersey is self-selecting itself into this treatment, which is problem. Then why? Because Pennsylvania, that is not a comparable case. We need to infer New Jersey counterfactual in New Jersey by doing something else, right? This simple comparison, cross-sectional comparison, is wrong then, correct? Of course, one thing you can do is you can control for such things, right? In a regression setting, it's just simply adding this as covariate. But the problem is, you know, like the people who are, they are called randomists, so you know, who actually more this experimentalists, they claim there is no, like, you never know the universe of all potential compounders, right? I just make this up, right? Textile, like labor competition. You can come up with something else, and someone comes with something else, right? And there is like, and this is not going to end, like, right? The number of potential controls that you can add, and this is just not manageable. So that's why they favor experimental methods. But others claim, come on, they are like, you know, like the relationship is, of course, they might be confounded, but of course we also have theory, right? Theory informs what potential confounders can impact the relationship, and you can just by just identifying those, you can just incorporate them into your setting, and that would give you unbiased estimate. So there is this like very lively discussion between observational data practitioners and experimentalists, and I can direct you some reading about this as well. But this is one idea. So you can simply control for this. And how are we going to do this? Well, let's say, for instance, one can also come up with this alternative explanation. Maybe in New Jersey, Burger Kings there are more Burger Kings, and Burger King, for whatever reason, is like they have different wage policies than other fast food restaurants. Then you need to control for restaurants. So here I'm just looking at the number of restaurants in the sample. So, for instance, in New Jersey, there are more Burger Kings, right? Compared to, well, maybe we need to look at the proportion. Yes, here's the proportion. So the proportion of restaurants across states. Although it looks like they are balanced, right? This could have been one problem. And what you could do, I'm just combining these two. So I'm just with the operations. What I do is just first I calculate the proportion. And you don't have to do this, so I'll just show it the end result. So the proportion of Burger Kings across New Jersey and Pennsylvania, KFC, Roy's, and Wendy's. So, I mean, one can argue that, look, in Pennsylvania, almost half of the restaurants are Burger King. What if Burger King is having this different wage policy, which might explain the difference that we just computed, right? So then what you need to do is, you can calculate for each state, for each chain, you can also calculate the outcome that we are interested in, right? And then you can actually look at the difference in means for each state and chain, right? So we can simply compare New Jersey Burger King with Pennsylvania Burger King, New Jersey KFC with Pennsylvania KFC, and this is more, right? Then this is more similar in terms of what we compare, and that's what I do here. So I mean, most of the operations are here because they are in long format, so I need to convert it in wide format so you can just see side by side. I'm not doing anything interesting here. I'm just putting them side by side. This is a problem, right? Data manipulation, like pivot wider and pivot longer. So yeah, that's you always need to check like how they are done. So anyway, so I'll just put them side by side and then calculate the difference. So before we only had one difference, two states. Now I'm having four differences, right? And this is done for each restaurant chain. So as you see, if you remember, it was around 5%. The first the point estimate before. So the difference in means are here. comparable except for Wendy's, right? So at least it seems restaurants are not, so it maybe, so at least this shows that restaurant chain is not explaining the outcome that we observe. And in a regression framework, so what I did here, right? I compare difference in mean separately, right? You could also do the same in regression, right? So just so this is the first 4% that I calculated, right? So who can tell me what intercept captures here? What is the intercept here? 32%. Ratio what? In Pennsylvania here, so New Jersey, exactly. So intercept here is the full-time employment in New Jersey. So and this is relative to New Jersey, right? So how are you going to interpret this? So this 4.8 is the difference in means as the estimate that we found at the beginning. So there was a 4.8% difference between New Jersey and Pennsylvania, and this is the coefficient there. And this is relative to New Jersey, which is captured by the intercept, right? So you can simply add chain as well. If you know, if you're like scared that chain is like the restaurant chain composition is different across states, well, simply add chains as well. And who can tell me what intercept captures now? So I have 3 restaurants here. One is missing. Why do we have one missing here? Maybe this is a hard question, but Burger King is missing. Where did it go?
It's the baseline.
Exactly, it's captured by the intercept. So this intercept is an estimate for so whatever we don't see here. So that's Burger King, New Jersey. So this is the estimate for Burger King, New Jersey. So that's 36% employment, right? So this is statistical control. So you know, you can always come up with something else. Maybe you might say, oh, it's the location, geographical location. I mean, I don't know New Jersey. If anyone knows New Jersey, one might tell, oh, in South New Jersey, whatever, for whatever reason, wages are whatever, right? So you can always come up with this. Well, you can add that too into your regression analysis. The problem is, of course, as I told you, there's no end. Right? You keep adding, and then of course you're gonna run out of degree of freedom. So so that's why a statistical control. That's one. I mean, that's a solution, but it's not a perfect solution. So there was something that we were not using, so leveraging. So it's actually the restaurants are recorded over time. We have 2 time periods here, before and after. I was just using after, but there is also a time like we could also use before time points, which also gives extra information, right? So we could also do before and after comparison. So hence there is this before and after design. So before we were doing, what we were doing is we were simply comparing New Jersey with Pennsylvania after, so that was cross section. Now I'm just gonna compare New Jersey after and New Jersey before. And you see where I'm going, right? I'm gonna combine. So before and after. So what's happening here? I'm just focusing only on New Jersey, and this is also nice in terms of the things that we control. Like anything that is constant in New Jersey is taken into account here, right? Let's say, oh, there is this pro-labor culture in New Jersey. That's historically, it doesn't change. It's constant. Well, then in this design, that's taken care of, right? Because we are comparing New Jersey with New Jersey. So anything that is constant, that is time invariant, is taken into account in this before and after design. That's the beauty, right? So so that's why, like anything that you can think of, time invariant things are taken into account here. So what do I do here? I'm just calculating full-time employment before the minimum wage increase. All right. And then I'm just taking the difference, full-time employment after minus full-time employment before, only in New Jersey. See, I'm just filtering by state, which is New Jersey. So before and after estimate is 2.3%. So it shows that after the minimum wage increase, employment in New Jersey actually increased by 2.3%. It is closer to cross-sectional design result, but it's a little smaller. So although time invariant things are here, taken into account, right? Like specific things to New Jersey. Time variant things are still, I mean, they can still potentially confound the relationship we find. Let's assume there is this positive technological shock in New Jersey. I don't know. Maybe they find this new technology, or they find oil, all right, in New Jersey. So maybe that thing is actually what's driving the change in outcome that we observe, right? And things that vary in time is not into if you don't control them in this design, before and after design, then they can still confound the relationship. We take care of time invariant confounders, meaning anything that is constant in time are taken into account, right? But anything that also varies in time are not taken into account in this setting. So they can still potentially confound the relationship. So that's the cons. So time varying confounding factors are not taken into account in this particular setting. But if we combine both these designs, before and after with cross-section design, then we can also potentially solve this time varying confounder problem as well. And this is the difference in differences. So combining these two designs potentially solve both time invariant and time variant confounder problem. Of course, again, we're going to be making one critical assumption, and if that assumption is satisfied, we can make causal claims. All right, and this is the difference. So how about we on time? So this is okay. How are you feeling?
Usually, we take a break at 1/2
Oldu.
the 20 minutes.
Okay, yeah, let's continue. So the idea essentially combines before and after with cross-section design. And there is this one key assumption. So unless this is satisfied, then we cannot make a causal claim. That's the parallel trends assumption. So the outcome variable needs to follow a parallel trend in the absence of theorem. And you might like, what is this? I'll show you what this is. But this is the key assumption. And whenever like you write a paper that uses the idea, you will have to show us that parallel trend assumption is satisfied. First, I'll show you a simple design, and of course, this is not going to happen a lot in your time, right? In your while you're doing research, and there are all these settings where there is variation in treatment timing as well, right? Let's say minimum wage, you're like focusing on the US again. Like different states adopt minimum wage increases in different times, right? They don't necessarily adopt at the same time. So if there is variation in treatment timing, we will have a problem, and I'll show you what the problem is. But first, just focus on this simple setup. Single treatment, 2 periods, all right? So this is actually 2x2 design, right? So we have 2 states and 2 time periods. So what we need to actually, so this is what we are interested in, right? So this is the potential outcome. So this is YIT1 is, so this is YIT1 is the outcome of interest for unit I at time t if the unit receives treatment. So this is New Jersey, for instance, right? New Jersey at time t, and this is New Jersey. Well, again, this is the counterfactual New Jersey essentially that we don't observe. So what we're gonna estimate is gonna be the average treatment effect, since we don't observe this, right, for each unit, because the counterfactual is not observed. We are gonna estimate the average treatment effect. So a little bit of notation, but one thing that, well, maybe I can just skip this, but what is important here is that, so this is what we are interested in. So the average treatment effect on treated. So condition 1 and getting the treatment, PI is equal to 1, so that's treated. The problem is we don't have this. Then how are we gonna infer that? So that's why we need this parallel trends assumption. So the time trend that New Jersey would have in the absence of treatment is gonna be inferred by looking at Pennsylvania, correct? So things would follow like the time trend, the time varying things are gonna be, so it's parallel, meaning that they don't need to be identical. So the things that are happening in Pennsylvania should just allow us to infer what would happen in New Jersey had there not been a treatment in New Jersey. All right, so well, this is from Imai's textbook. So it's very simple 2x2. So what do we have here? So before we have New Jersey, and then we have Pennsylvania. And then we have these two, so we have essential 4 time points here, right? The 4 data points, this, and this. So, so what we infer, so Pennsylvania is useful because it allows us to infer what would happen to New Jersey if there were no treatment. So the parallel trends assumption essentially says that New Jersey would follow something similar to Pennsylvania in terms of time trend. So see, that's why it's parallel. So this tells us by looking at Pennsylvania, we compute this. Okay, things that like employment would decline in New Jersey if there were no minimum wage increase. So this Pennsylvania control allows us to infer the time trend. All right. Essentially, we are again just subtracting cost from credit. But the Pennsylvania will allow us that time component. Yes.
Correct me if I'm making a mistake. So we have for New Jersey, we have before treatment and after treatment.
Yeah.
The other side of Pennsylvania that we haven't applied any treatment.
Yes.
So we have that state. So right now you're saying that we want to infer, let's say, if we treated that, let's say, rule in Pennsylvania, right? So that's the thing they're saying we missed, right? You missed the after treatment for Pennsylvania.
Yeah, well, so yeah, so we observe Pennsylvania before and after. The only problem in Pennsylvania is not treatment, but we have 2 data points there too. The problem is, of course, there is no direct test of parallel trends assumption, right? We don't know whether New Jersey would follow a parallel trend. Well, there's a way to test it, but with 4 data points, you cannot. I mean, there's a way to. I'll show you how to do it. But in this figure, you cannot simply claim New Jersey would follow a parallel trend. What you need to have is more data pre-trend. So you need more data. You need to go back in time, right? And multiple data points here, and just look at how they would behave. Maybe, well. The way they are now written, like they're drawn, it shows that they might not follow a parallel trend, but you need multiple time period, like you need data points from pre-trends, and you can compare them. If they are parallel, then you can conclude, okay, if they are parallel pre-trend, then you might say, okay, they would also follow a parallel trend after the treatment, if there were not treatment. So that's the basic. Maybe I can. Let me just quickly show you a figure. Something like this. So if you had multiple data points before trend, so look, so treatment comes here at time t, let's say, and just look at what's happening before. And 2 groups are, and let's say this is the employment outcome. They are kind of following a parallel trend. Of course, there's more formal test here. But we should, by looking at that, you can claim if there were no such treatment, probably treatment and control would follow a same trend. So parallel trend assumption can only be tested by looking at these pre-trends. And if they are fine, that's a good thing. Yes.
At the beginning of the presentation, we talked about the correlation issue. Now we are like comparing 2 different places and trying to infer if we didn't make a change in one, how would it change? Right?
So I think I understand your point.
So we are looking at 2 places, and one we made a change in one.
Yes.
And since we have like pre and after issue for one in which we made a change, we want to compare it with other city and
where there's no change.
Yeah. So the problem is that what about local changes in the place which didn't make any change? Like it's all about correlation.
I see your point. So that's the thing. So time varying confounders, like I don't know, technological progress. So if parallel trends assumption is satisfied, that means whatever is going on in Pennsylvania, like those time varying things, are gonna follow the same trend in New Jersey as well. So that's the assumption. If parallel trends assumption is satisfied, let's say, I don't know, technological growth. If that's like 2% in New Jersey, if it's 2% in Pennsylvania, that would and that should be similar. At least the trend, like the difference should be 2% as well in New Jersey. So that's what I mean by like those time varying confounders should follow similar trend. And that's the whole purpose of Pennsylvania. We infer that time varying confounder, the time trend, and time trend is caused by all these time varying things going on in Pennsylvania. That's why we have Pennsylvania. We don't have Alaska, right? The logic is that okay, this is comparable enough to New Jersey.
It is enough.
Yes. So and if it is not enough, parallel trend assumption would be violated. So that's the key. So that's why this is important. Like you need to show me something not like this, but something like something like this.
So the key is to find a place which is similar to the place you are comparing.
Exactly. So
you will minimize the difference.
So if this control group is similar enough, then they would follow a similar time trend pretreatment. Like pretreatment, you know, if you just like plot them, if they are different, if you plot like if you put New Jersey and Alaska, probably pretrends are gonna be so different, right? Then parallel trend assumption is violated, then the ID is not valid. Yeah.
So Burger King then numerical variable, right? Like is the numerical variable in that context because you cannot balance out like New Jersey. Right? Services there. Like, so how are you gonna balance that?
What do you mean balance?
Like you cannot like make the exact same assumption.
They're not going to be exactly the same. So the thing is that on average, these things should be similar. So on average, meaning that of course, if you just pick two restaurants randomly, they're going to be different.
So
but if you average them out, they're going to be similar. Yeah,
okay.
That's the reason. So that's why what we are estimating is average treatment. This is what we are estimating. The quantity of interest that so that's called estimate. Estimate is average treatment effect, and that's sample version, sample average treatment effect, which is essentially, I mean, don't bother the notation, but it's essentially you have outcomes for both. Just take the average. So and well, the average, of course, this is the size of the treatment group. So this is average treatment effect for the treatment. So I mean, in experimental design, so in RCTs, normally the average it's ATE, so this is average treatment effect. So because in experimental setting, we make sure, thanks to randomization, control and treatment groups are similar on average. Here, we only use that treatment group so we only use that time trend component, right? So again, here it's like less ambitious, like what we estimate in that sense, right? It's average treatment effect for the treatment. So in experimental setting, they are identical. Why? Because well, these like two groups in experimental setting, they are comparable directly. Here, Pennsylvania is only comparable in terms of like this time trend, like that's the time trend that we are using. I mean, they are like different states, but it's similar enough so that we can infer the time trend. So that's why it's ATT. So I wish treatment effect for treatment. That's what we are estimating here. So that's the estimate. This is a nice. So estimate here is average treatment effect on treatment. And we're gonna have estimate, right? The ID estimate is gonna be well, we're gonna have an estimate for the estimate. An estimator in this case, right? That's just the recipe. Like, how are you gonna estimate that? In this case, it's gonna be the ID, but you can also use other things, right? So those are just the jargon. So just have that picture in mind whenever people talk about estimate, estimator, estimate. All right. Any questions? So just a super simple. What means like what is the ID? It's actually the difference in differences. So here, difference in New Jersey and difference in Pennsylvania. Why Pennsylvania? Because well, we cannot observe the counterfactual New Jersey. That's why this part is thanks to parallel trend assumption. All right. And like for instance, imagine we have this very simple 2 by 2. All right. How are we going to calculate difference estimate here? So let's first look at cross-section design. The first thing we did was this, right? So that's after minimum wage increase. It's essentially 60 minus 55, right? So this is cross-section design estimate, 5%. Before and after, the second thing we did, that was just New Jersey pre and post. So that's well, that's 60 minus 70, right? So there is a 10% decline. The idea is that essentially difference in difference between two. And look how that's different from before and after, for instance. Why there's a difference of 5%? It's because we see, if you look at Pennsylvania, you see after the minimum wage, so because Pennsylvania is not treated. The time trend follows, like, you know, these all local factors are impacting the employment in Pennsylvania in such a way that there is an increase of 5%, right? Yes, pre and post. Which shows if New Jersey was not treated, New Jersey would also have this 5% increase. So that's why we need to subtract that too. So that 5%, because we already have 10% decrease, and that's also there was going to be a 5% increase in the absence of treatment. We add them up, well, we subtract it, in this case, it's minus 10, minus 5, so that's negative 50. Hence, so that's the time trend we use here, all right? Because positive things would happen to New Jersey if there were no treatment. So that's the idea, all right? Any question? Now we can maybe start. Well, yeah, I'll just calculate the ID from the, well, maybe let's do this too, and then I'll start. So, well, how am I gonna, well, of course, this is the point estimate. I'll use regression design just because point estimate is not enough. We also need to have some sort of an estimate for the uncertainty, hence we need the standard errors as well. But how am I going to calculate the difference in differences? Well, so we have full proportion of employment after and before. If I just do it for each state, right? Then I take the difference. So this is the difference and difference estimate. It's 6%. So if you buy parallel trends assumption, which with 4 data points we cannot test it, but I'll show you like other examples where we can test it. If parallel trends assumption is satisfied, minimum wage increase in New Jersey actually increase employment in New Jersey, as opposed to this basic 101 econ theory, right? By the way, there are a series of papers after this paper, and still there is no empirical value. If anything, there seems to be some like positive impact, but there is no negative. So the econ literature, like credible research designs, show that minimum wage increase actually doesn't cause decline in employment. Possibly because of demand effect, probably. But for instance, read Cengiz et al. QJE paper, for instance. That's the, I think, the latest of series of papers. So anyway, at least if anything, the impact is positive. All right, and I'll of course, well, I'll just show the same thing with OLS so that we can also estimate the uncertainty for the point estimate. We can do after the day. All right. Yes.
Is it possible, rather than choosing pre and post data of different states, maybe we can use the data of same state and collecting data from another time point?
Well, this is kind of what we did with before and after, with only two time points. You can just extend it, but the problem is going to remain. Time varying confounders, you won't be able to solve that, right? With this, like if you observe New Jersey over time and you just like compare, across time changes, time invariant things, right? Things that are specific to New Jersey but do not vary over time, they are all controlled. Like there is no time invariant confounders there, but still time varying confounders are going to confound the relationship. So, for instance, technological shocks that vary in time, which might explain the increases or decreases in unemployment that has nothing to do with minimum wage increase. So, positive shocks could impact both, right? Technological shock, increase wages and also employment. Well, if you just don't take that into account, then the estimate still is going to be biased. Right?
Can we use difference in different tests? The example that I.
You cannot, because you need to, so you need also other units, like for instance, you need some sort of Pennsylvania observation. That's the thing with the idea. It combines before and after with cross-section design. So we need a counterfactual for New Jersey or time trends. So that's Pennsylvania. But you can also have multiple units, which I'll show you like more complex design. But in the simplest version, it's you need another like Pennsylvania, something like that.
don't have this kind of, we can create our scientific one, yeah.
Synthetic. Oh, that's another. Yeah, that's another. Yeah, synthetic. Like that's another research design. You can create your synthetic. And that's actually, yeah. If you have, like, for instance, data points from across states, and you can create a synthetic New Jersey, and you can just compare New Jersey with that synthetic version. But the problem is, how are you going to construct that synthetic New Jersey? That's going to be function of observed covariates. And that's essentially, I mean, similar to what we are doing here. So, like, synthetic New Jersey is going to be based on what? Population, I don't know, technological progress. It's going to be function of observed things anyway, which is going to be, I mean, the idea is also like, I mean, it's kind of, it's, the whole point is just find something comparable to New Jersey.
What idea about that? Like, let's say we found a place which is not very close, but it's pretty close together. But there are some unique change for this place. Can we just to make it similar to the city we are comparing with? Maybe we can just make the weight of this local features in the, I don't know, model. I don't know what's the background.
What do you mean by?
Maybe. I don't know. I can explain it in mathematical side, but maybe we can.
But the problem is, like, how are you gonna know what are the things that is like causing increases or decreases in employment? You can have like millions of variables that impact that, right? The nice thing with the idea is, whatever those time varying confounders, if you find a similar state to New Jersey, in this case Pennsylvania, the combination of all these things you can think of are going to produce a time trend. And if they are similar in New Jersey, like Pennsylvania, then we can use that time trend to infer what would happen in the absence of people in New Jersey, so that you don't have to worry about those specific things. Yeah. Yes.
There we have similar states and we have similar color trend. But what if the trade one state affects the another?
Yes, that's another issue. There will be, this is a violation, suit by assumption. So stable units are treated. So what could happen is, there could be, for instance, let's say you are living in New Jersey or Pennsylvania, then just neighboring state increase the minimum wages. Well, you just simply move there, right? So the impact, so the treated unit, right? So if you're like this treated unit can impact untreated ones. So suit by assumption could be violated. Just read the paper. They talk about this as well. Yeah, I mean, they got Nobel Prize. They took that into consideration, but that's an important yeah. Yes.
How do I convince that the state that I choose is the best state for satisfying the parallel trans assumption? Like myself. And
so one thing is, you can always check whether that's like comparable, but that's going to be theory driven, right? So for this case, for instance, it's employment, and they are focusing on fast food restaurants, and it's the neighboring state. So that's not Burger King in Alaska, right? So that's going to be informed by theory and the design research. Right? But obviously, if you're wrong, if that's like totally different, so I'll show you one example from one of my papers. Well, after the break. So I mean, then parallel trans assumption would be violated anyway, which shows that okay, this is not a good comparison in the first place.
So the way to go is kind of try a few neighboring states to see which one would be the best to kind of do all.
Yes, in a way. Yes. I mean, if they are comparable, then there shouldn't be any pre-treatment like differential trends. They should follow a parallel trend. That's the whole thing with parallel trans assumption. They need to be comparable before treatment, so that we can infer what would happen after treatment by looking at the control group. Okay, let's give a break.
Okay, so right now it's 2:35. Be here 15 minutes later, so 2:50 you have to be.
Okay, so well, I showed you the difference in difference estimate by simply calculating the differences and taking the difference, right? But of course, one problem here is we don't observe the uncertainty for the estimate, right? That's 6%. What is it statistically significant? I don't know it, right? So that's why regression framework is useful as well to uncover the ID estimate. So in this canonical simple design, it's fine to use OLS. Like when we have more complicated designs, no, right? We'll see that. But in this 2x2 canonical simple design, the ID estimate is essentially captured by data 3. So what is DI? DI is so this is just this is 1 for New Jersey, all right, and 0 for Pennsylvania. And cost is just 1 after minimum wage increase and 0 before minimum wage increase. And this is essentially cost, which is 1 DI, which is so New Jersey cost. So this is cost New Jersey. So this beta 3 is gonna capture this. And if you don't believe me, I'll show you that this is indeed the case. So what do I do here is just converting the data from wide to long format. All right. So because I need that panel data structure with the OLS, right? That's why I'm skipping this, but you can just do it yourself. Once I have this full like long data format, then I'm just fitting this simple regression. All right. Look, this is beta 3. So the estimate for beta 3 is 6.1. And go back. 6.1. All right. So this is essentially what we calculated can be recovered by OLS as well. And now the nice thing is we have also the uncertainty, the estimate. So we have the estimate, but there is also uncertainty around this estimate, and we can quantify that with standard error. And what's your conclusion? What can you conclude based on this this result? Does minimum wage affect employment? At least in case of fast food restaurants. Yes, anyone? Yes.
Not that much, because of R squared, degrees of freedom, and the general denominator very low.
So R square is not an issue here. Not because of R square. Because of maybe that what were the other things you mentioned?
Degrees of freedom.
No. What else? You also said
general,
what?
the statistics like for the period is very low. Mine is like they're very small. So
Exactly. So that's what I was interested. So this is the coefficient you were going to say.
I was gonna say status now that's coefficient we cannot.
Exactly. So it's 6%, but uncertainty is also high. Hence the p-value is what's p-value? What is p-value?
The level of the price when you
Yes. So p-value is actually a probability. So we observe this. So p-value is the probability of observing something as extreme as the one you observe under the null hypothesis that this is 0. So okay, I'm observing 6% here, right? But is this very extreme or not? So this is actually the probability of observing something as extreme as this, and this is in absolute terms because we can also observe negative minus, right? Negative 0.6 and even more negative, right? So that's why it's if you like the sampling distribution, you also like you need to take the probabilities from both sides, from positive and from negative side, and you just multiply by 2. So that's two-sided p-values. It's the probability of observing something as extreme as this one under the null hypothesis that beta 3 is 0. So that's the p-value, and it is 18%. So it's not that extreme, meaning that we are not that surprised, right? So this is and that's why if we use this conventional thresholds like 5%, right? This is not statistically significant at 5%, even 10%. Hence, we cannot conclude that minimum wage, at least it has no impact. It's also contrary to basic Econ 101 result, right? And if anything, it's positive. So anyway, so this is the DID estimate. But as I told you, in order to believe that this is actually the causal estimate, so the causal impact of minimum wage on employment, we need to have this parallel trend assumption to be satisfied. But there is, how are we going to test this, right? Because parallel trend assumption tells us that Pennsylvania, New Jersey would follow a similar time trend in the absence of treatment. But how are we going to check this? Because we don't observe New Jersey counterfactual, right? Well, as I told you, we can look at pretrends. So the key thing in the idea is you need to have multiple data points before the treatment happens, so that you can compare these two groups over time and just keep track of them if they follow parallel tracks, right? Let's say, do I have marker? That's also, you guys, someone told me that you get excited when I write on the board, but I don't have a marker. Well, I had one, but it's back. Well, you know, like, okay, so we have, oh, yes. Someone is prepared.
We want to as well?
No, it's fine. So let's say you have like treatment and we are tracking, you know, employments. So T minus 10 to report that, T minus 9, right? So there is a slight increase. Then you would expect the same time trend to happen in the other as well. So let's say this is treatment, this is control, right? So then what happens? So maybe in T minus 8, this happens, then similar thing should happen. Well, they should, you know, you get the point, right? They should just follow similar trends. And then after treatment, well, treatment is just maybe, right? So, and this follows, let's say, this flat line, and this just increases. So what this tells us, this part is, okay, then if this group was not treated, it would follow something parallel to this line. And how do we conclude this? By looking at the trends. So they were following a parallel trend. Then that means they would have the same time trend after the treatment. And what is the DID estimate? It's the difference between these two things. All right? This is DID. So that's why a parallel trend assumption is critical. So of course, you know, visually tracking whether they are parallel or not is not very formal. So what you can do is something like event study. Has anyone heard about event study? You don't count them. Again, so event study is essentially fitting a more flexible model. It's like the idea, but you have multiple time periods. So for instance, let's say we have yearly or monthly, let's say, or yearly employment data. You can fit something where like you can estimate the impact for each year separately. Then what this tells is if parallel trend assumption is satisfied, all the point estimates before treatment would be null, meaning it's going to be closer to 0, while after treatment, they're going to be negative or positive, right? Whatever you expect. So, and this is just the so it's from negative k to minus, so because these are essentially time dummies. All right, let's say these are years. Well, of course, in order to avoid dummy variable trap, you need one baseline. Essentially, the practice is you take one, let's say it's yearly, 1 year before treatment. Let's say New Jersey treat, so it happened in 1992, right? You take 1991 as the baseline, and you just look at time dummies. So you just calculate the difference between these two yearly, and just plot the point estimates. So let's say this is 1992, right? So treatment happened here. So the difference between them for each year. So you just, let's say you start in and then 1991. Simply plot the point estimates. Well, let's say this is 0. So the point estimate and the confidence interval. Sorry for my horrible writing, but so it should be null before treatment. If parallel trend assumption is satisfied, that means there is no difference between them. But after the treatment, then you should find whatever, like if it is positive, it should be positive. If it is negative, it should be negative. So this is more informal way of testing parallel trends. Just simply look at what the outcome will be between two groups over time. And for instance, here it looks parallel, right? So then you can conclude, okay, there is a parallel trend assumption satisfied. Or you can do something like this. It's event study approach. But this is from one of my papers. So what we do here is we are looking at trustee mayors, and we are comparing their way. So because they distribute state contracts, right? So for those who don't know the context, in southeast of Turkey, there are some mayors, elected mayors replaced by trustees. So we compare these trustee mayors with AKP elected mayors. So elected mayors from the government party in the same province. So again, it's like similar to New Jersey, Pennsylvania comparison. We are comparing kind of apples and apples here. So they are operating in the same provinces, southeast provinces, and we are just looking at, you know, what happens when trustees are they take over municipalities, and the outcome here is a sealed bid auction. This is just the most transparent way of delivering state contracts. So state contracts, you can use just different methods. Sealed auction is the one that is most transparent. What we see here, for instance, just after trustees take over, look, before trustees take over, these are essentially the differences between elected HDP mayors, right, or HDP mayors, Kurdish elected mayors versus AKP mayors. And they are kind of, you know, there's no difference between them in terms of sealed bid contracts. But after trustees take over, it suddenly, look, this is 0 times 0, 1, and you know, this is when they take over. Suddenly you see this decline. So if you show something like this to me, and I would buy your parallel trans assumption. I'm not saying this because this is my paper, but this actually, you know, shows parallel trend assumption is satisfied. The way that HDP elected mayors and AKP elected mayors behave were similar before trustees come and take over these elected municipalities. They suddenly change the way they distribute state contracts. All right, so you need to do something like event study in order to formally test the parallel trans assumption. All right. Any questions? All right, so moral of the story, parallel trend assumption is key. So you can generalize this simple 2 by 2. Like here, for instance, this is not simple 2 by 2. There are different municipalities, trustees take over in different times. So this is a complicated design. Well, unfortunately, well, maybe fortunately, you cannot use OLS in this more complex designs, staggered, what we call staggered designs. If there is variation in treatment timing, meaning that we no longer have New Jersey and Pennsylvania, but we have, let's say, 50 states. New Jersey adopts in 1992. Let's say California changes minimum wage in 1994. I don't know. Nebraska changes 2000, right? There will be differences in treatment timing. So actually, I mean, normally you could extend the OLS, like the one I showed you. You can extend that 2 by 2 to multiple time periods and units with just 2 simple fixed effects. So unit fixed effects and time fixed effects. By fixed effects, I mean you can also adapt like as dummies. It's essentially the same. Time dummies and unit dummies. So in this case, if we are talking about minimum wage in US, state fixed effects and year fixed effects, then this beta is gonna be the DID estimate. But this is gonna be biased. So the beta that you estimate here is gonna be biased if there are variation in treatment timing, meaning different states adopting minimum wage increases in different times. Second, if there are effects are heterogeneous across units. The impact of minimum wage increase on state X differs from state Y. So if these 2 things satisfy, which almost, I don't know, always, then you cannot use 2-way fixed effect regression because they're gonna be biased. And this is actually a super recent literature on the ID. Like last week or 2 weeks ago, there's another paper that came out, but all these series of papers, they just warn against using 2-way fixed effects, and they just suggest alternative estimators. But I'll show you why we cannot use the 2-way fixed effects. Just give you the logic. But this guy, he's an economist. He has a very nice website where you can, like, he tracks the ID literature. So this is super recent. Like some of the papers are not even published yet. As we talk, there is probably a new paper coming out. Like this is super active research area. Like econometricians are working on this. But moral of the story in all these papers is that in a staggered design where there is variation in treatment timing, you cannot use 2-way fixed effects. In the canonical design I showed you, that simple 2 by 2, it's fine. If you know, every unit is treated at the same time, that's fine. But in other cases where this doesn't happen, like in this case, we, for instance, this is not coming from two-way fixed effects. This is coming from a different estimate, and I'll show you what that is. So, DID two-way fixed effects, so it gives biased estimates. So what these papers, so there is one accessible paper, well, because I mean, it's accessible because if you look at the methods paper, well, good luck. They cannot, I mean, the math can be quite heavy. But the moral of the story is that two-way fixed effects are essentially, because now we have multiple units and multiple time periods, it's essentially 2x2s. It's just different combinations of 2x2s weighted by weighted averages, right? So it essentially combines different 2x2s. If you do this, if you extend our canonical design to multiple time periods and multiple units, what beta here captures is the weighted average of all 2x2s. And I'll show you one example. And this is actually, the example comes from this nice paper from Journal of Financial. So these guys, they just summarize the problem nicely and show you it's like some simulation results and everything. You can check this paper. For instance, assume we have three groups from T0 to T. And there is a never treated group, like Pennsylvania, that got never an increase in terms of minimum wage. Then there is earlier treated group, K. Then later treated group, so which means we have here 4 different 2x2s. The problem is when you do two-way fixed effects, some comparisons are bad comparisons. So what happens is that, so for instance, if you compare K, so early treated group with L, late treated group, from the window from K0 to T0 to 3L. So here, for instance, if you compare them, L is essentially serves as control, and K is the treatment group. So this is fine. But let's see. So but this is fine. Why? Because L is not treated yet, and K is the treatment group. So you can compare. So L, although L is going to be treated at some point later in time, the moment that we compare, it's like Pennsylvania, but at some point it's going to turn into New Jersey, right? It's going to be. But some comparisons are actually comparing. So are taking early treated groups. So this is earlier treated group is K. So K is treated as control, while L is treatment. But the problem is K is already treated. So you are taking a treated group as a control group, which means you are actually comparing, like it's already treated. So you cannot take that as a control group. So that's the problem in two-way fixed effects. Some of the 2x2s you compare, some of them actually involve these forbidden comparisons. And if you go and read these methods paper, they call this negative weighting problem. Why negative? Because you use them as control while they were already treated. I mean, you cannot use treated group as control group. So that's the problem. That's the heart of the problem that two-way fixed effects are causing. So then what are you going to do? Well, the fix is easy, right? Just don't use those forbidden groups as control groups. So all the estimators you see in the DID literature, they actually rely on this fact. So they don't use these treated groups as control groups. They just construct clean controls. Those controls, for instance, can be never treated groups, because since you have multiple time periods and time groups, right? Some states, for instance, are never gonna adopt a minimum wage increase, and they can always serve controls. Or you can also use late treated ones. They are earlier periods, right? They are also not treated. So you can also use them as controls up until the time when they are treated. So as long as you find these clean controls, then you won't have this negative weighting problem. So for instance, most recent paper that came out like 2 weeks ago or so, it actually still uses OLS, but the only difference is that it just excludes those bad controls from the estimation. All right. So that's the idea. So whenever you see different estimator, just keep in mind that of course they're gonna differ. They're gonna differ in terms of what you compare, because sometimes you can't, depending on what you do. For instance, you can take never treated groups as control, but in certain samples, everyone is gonna be treated at some point, right? Maybe every state is gonna adopt minimum wage increase at some point, which means there won't be any never treated groups. Then in that case, you need to use late treated groups as controls, right? So there are all these differences in terms of what you estimate. So one of the most famous one is Calare and Santana 2001 estimated. So essentially what it does is it identifies cohorts. So cohorts are, let's say, California and New Jersey adopted this minimum wage increase in 1992. Those who got treatment at the same time are treated as one cohort, right? So they identify those group-specific ATPs, all right? Of course, you need to find some proper controls, and they need to be clean controls, meaning that either they need to be never treated groups, or you can use early time periods of the later treatment, correct? So once you have these cohort time specific treatment, so the cohort or specific ATPs, then you can combine it in like whatever way So one is you can simply take the weighted average to have one ATT as we found in the previous the canonical design. Or you can also like do all other things. Like you can report them differently, or specific ATTs can differ, and you might want to report them as well. So it's up to you, and it's also up to the research design. So for instance, here, like in this example, for instance, what we did after showing this, we just combined them into one ATT by taking the weighted average. So, but of course, depending on the cohort, the impact might differ a little, right? So you might also want to report that as well. This is what I mean by, like just take these cohort specific ATTs. So then what's going to happen, for instance, there will be one ATT for California and New Jersey, for instance, because they are one cohort, right? And then let's say there is Washington and Alaska adopting the minimum wage increase in 2000. They're going to be one cohort, and they're going to have their own ATTs. Well, then you can just combine them, right? Take the weighted average, and that's going to be the ATT. So that's going to be average treatment effect. Or you can again, report them separately as well. And of course, like this avoids the problem of two-way fixed effects, that negative weighting problem. That forbidden comparison problem is no longer here because the solution to that is in this paper, right? It doesn't use those forbidden comparisons. And it's also more transparent. You can also see cohort specific ATTs, and you can just combine them in whichever ways you want. And there is this there are alternative estimators, as I told you. So for instance, Calave and Santana, like the recent paper I mentioned, I forgot the paper now, but probably it's going to replace Calave and Santana estimate because it's easier to estimate. So this is a very active research area. So, but moral of the story is, not to use those forbidden comparisons. Just know this. And whenever econometricians just use this negative weighting problem, it's essentially all these bad comparisons. The problem. So there is another good review. This is also working paper. What's trending in differences? So this is like last year, and it's already out of date because of the most recent paper. So probably gonna update their paper as well. So how are you going to use Calave and Santana? Well, luckily we have already our paper, our package. Sorry, it's DID. I'll just use the example data set that they have in their package. So this is again minimum wage example on this time youth employment, and it's county level. All right. So these are like each row is a county, and of course, depending on where these counties are, there is variation in treatment timing. So one county is in New Jersey, which means in 1992 there's an increase, right? And one is in Pennsylvania, so on and so forth. So there are differences in treatment timing, right? But if you look at them, so there is just this thing where you need to put your data in a particular format, just because how it is written. So it needs to be in long format, and you will need an ID and time variable. And also, you need this group variable, which is first tree, and this is just the time period, like when that count is treated in this case, for instance. And if they are never treated, you need to put 0. If it is NA, it's gonna yell at you. Well, it's just the way it is written by Calavay and Santana, all right? And yeah, well, you can always check the documentation anyway, but these are the things you need to be doing. So for instance, if you look at first here, there are 1,545 counties that are never treated, which means they never saw in the time period that we analyzed, no minimum wage increases there. In 2004, like 100 counties, 2006, 200, and so on and so forth. If we use two-way fixed effects here, what would happen is that, for instance, those who are treated in 2004, let's say Los Angeles County, let's say assume that it is treated in 2004, it would serve as control group for counties that are coming in that are treated in 2006 or 2007, which we shouldn't be doing because it's already treated. So that's the problem with two-way fixed effects. And for instance, I replicated one of papers written before this method became published in a good journal in one of my class. When you replicate it using this method, all results they just went away because two-way fixed effects it's just a bias estimate. All right, so that's the problem. And I mean, you can try go back and look at early 2000 differences papers if you find the data, and they would all use two-way fixed effects. Replicate it, and it's a good exercise. Replicate it with these new estimators. Some of them are going to go away. They say 95% of that are going to go away because there will be variation in treatment timing, which will include bad comparisons, and also there will be heterogeneous treatment effects as well. So results are going to change for sure. Anyway, so this is something like you need to have this first treat variable as well, and it's essentially ATT GT. So for specific ATTs, what we are estimating here. So and the syntax is library specific. This is young employment. G name again. This is the time when each cohort is treated, and if it is never treated, it's 0. And then ID name, just the ID variable for units, and it's just a time variable. And then you can also add covariates here. I didn't add any covariates here, and this is the data. So summary. So you get something like this. So what is this? So look, 2004. So 2004 group. These are essentially 100 counties that are treated in 2004. So those are the counties that witnessed minimum wage increase in 2004. And you will have all these cohort-specific point estimates. All right. So for instance, this 2004, 2005, this point estimate, for instance, here, it shows what happens to counties in 2005 that are treated in 2004. So this is 1 year after treatment, correct? That is for 2004. But in 2005, for the group who are treated in 2006, this group is not treated yet, right? Because they are treated in 2006. So for instance, for that group, if you want to look at post-treatment, so this is the coefficient, right? Of course, this is a bit tricky because they are all these cohort specific. You can combine them. So GGDID is part of this DID package. So it will combine, for instance, so first, for instance, you can just look at each group separately. And as you see, it also colors them differently. So 2004, so if it is blue, it's treated. If it is red, it's not treated yet. And you can also, for instance, look at 2007. All these red also serve as a parallel trend assumption check, right? It's similar to this event study approach, right? So you can see, for instance, there is no there's not much like this. They all, but post treatment is also kind of null. There's something going on with 2004 maybe, but other than that, there's no impact. So you can also aggregate these group type average treatment effects into one single ATT or something like this. You can also combine them, right, across years as well. So with type dynamic, that's what I did here. So now this is the event study approach that I mentioned before. This is also useful to test the parallel trends assumption. If parallel trends assumption is satisfied, what would we expect is pretrends. So pretrends -1, -2, -3. These are so they are all gonna cross zero, right? They're gonna be null. And if there's an effect, you would find statistically significant results after zero. And there seems to be here, right? So 1 star here means 95%. So these are simulated confidence intervals. So they are not analytically computed ones. But these are coming from bootstrapping, which is, well, it's just a way of calculating uncertainty around the estimate. So bootstrapping is just like you just randomly sample bit replacement, compute it, let's say 1,000 times, then you will have a sampling distribution. Then you can just look at the uncertainty of that distribution, right? You can just focus on 95th percentile, right? So that's and also 5th percentile, or well, that's going to be 10%, but you can also do 97.5 versus 2.5, right? So it's essentially, let me just. So bootstrapping is, so let's say you run this 1,000 times, you will have 1,000 data, and you can just have this distribution of data, right? Then that simulated confidence intervals, just look at the 97.5th percentile, and then, right? So these are, you will have some data here. So that's going to give you 95% confidence interval. It's only calculated with bootstrapping. So this allows us to visualize the uncertainty as well. All right. So this is the result. Look, pretreated periods, they are all nulls, which means parallel trans assumption is kind of satisfied here. Then after minimum wage increase, there seems to be a decline, right? It's clear. After first year, so year 0 is the year they are treated, right? Young employment, at least in these countries, seem to decline when there's an increase in minimum wage. So that's the conclusion we can conclude. Any questions so far? Is it clear? So you don't have any questions because it was complex or it was super clear? I want to believe it's the same. I mean, it's essentially the same, like what we did in canonical design. The only complication here arises because of two-way fixed effects, but then there are other estimators that don't use these forbidden comparisons. And again, the idea is similar. Like you need to somehow just visual, you need to show us the parallel trans assumption is satisfied, and this is one way of doing it. All right. Okay, so this is your crash course on the idea, essentially. Again, as I told you, there are all these different estimators. When design is staggered, meaning there's variation in treatment timing. But if it is canonical, simple 2 by 2, I mean, two-way fixed effects is going to be okay. But other than that, you need to avoid using two-way fixed effects. All right. Any questions? So for regression discontinuity, I'll be quicker. I don't want to take too much of your time. So this is essentially another design that allows you to tell a causal story using observational data. And I'll just show you, I'll just jump to an example again from Imai's textbook. It's a paper published in APSR. The question is how much politicians can increase their personal wealth due to holding office. So that's the returns from an office. And data is from British Parliament. So, I mean, it's obvious, right? We cannot simply compare members of parliaments with commoners like us, right? Because if we compare the wealth of elected people with wealth of commoners like us, they're going to be different. But it's not because of they are holding office, right? It might be because of all other things. Like in Turkey, if you want to be a candidate running for a member of if you want to be a member of parliament, you need to be rich, right? You need to fund your campaign. You need to have connections, which make them already different from from commoners like us, right? So we are not compatible with them. Maybe that's a good thing. So then what are we gonna do? RDD is one solution here. So the idea is, well, there are all these people who are running for office, right? You can simply compare those who barely won elections and hence got a seat in the parliament with those who barely lost the office, hence they just didn't get the seat. The idea is that these groups, like those who narrowly won versus those who narrowly lost, are competitive, meaning that if you just look around that threshold, they are more compatible. It's like an experimental setting, right? Because when elections are super close, it's kind of randomization, right? It's just like God flipping a coin and determining who is winner and who is not. Because although these people are spending a lot of money, they cannot, if we are talking about a functioning democracy, they cannot perfectly manipulate the result. Of course, you're going to spend more money, and you'll spend maybe campaign spending and everything, but so do your opponents who barely lost, right? So it's kind of that like narrow, like barely winners and barely losers are more comparable. Those, for instance, if you lost by 50%, well, then you are not comparable to the winner. But if you are just focusing on that narrow window, then they are more competitive. Of course, the problem is like, how are we define that narrowness? Like, how are we going to define that, that window? And how are we going to fit, essentially fit it, like, how are we going to fit regressions or like some, we need to fit the data, right? What's going to be the model that we're going to be using? So essentially, all RDD literature revolves around two questions: window size and how to fit given the window size. All right. And once you figure them out, well, you have your RDDS. So again, the data comes from Imai's library. So here, what we're going to compare is, so each row is either NP or a loser. But they barely, like some of them barely lost, some of them lost by a wide margin. So losers and winners is our data set. And what we have is, thanks to British case, apparently when MPs need to declare their assets, and apparently so when losers, so there's this legal something where when you die, your wealth is published in some weird places, and these if you go read the paper, they also they manage to kind of track the personal wealth of losers as well. That's the tricky part in terms of data collection, right? Losers, they're who knows where they are. So that's the difficult part. But they somehow manage to collect the data, and ln gross, ln net. So these are just logged wealth in terms of pounds. All right. First, I'll show you very simple RDD where I'm going to be fitting two regression lines. One is for losers, one is for winners. Since I have two fitted lines, I can simply predict what would happen at the margin, which means like, when margin is 0, what would happen? Because one is coming from data points from losers, and one is going to be coming from data points from winners. Then the difference between them at the threshold, which is margin 0, will give us an RDDS. So this is going to be the simplest, like the most simple one. Of course, the problem is like there will be problems. I'm not going to define any window. I'm not going to define any, it's just a linear fit, which might be not a good fit or not. So that's like a whole point. But and I'll do it for Labour and Tories. So two major parties in the British Parliament. All right. First, I filter the data, Labours and Tories. Now I have two data frames, and I'm just super simple linear regressions, right? Margin. So this is 0. So this is positive. If this is positive, that means you're a winner. And if it is negative, that means you're a loser. All right. So winners, losers, winners, losers. So I have 4. Well, since I have 2 parties, for each party 2 fitted lines. So that means 4 fitted lines, right? Then what do I do? So you don't have to do this, but there is this nice data grid function from Model R. It's just if you want to predict using a model, you can use this, but you don't have to. You can create your own data frame and use it with predict function, right? So what data grid does nicely is it looks at the data and extracts the observed data points to make the predictions. Or you can also create this by yourself, so it's fine. Yeah, that's what I do here, for instance. I just look at the data for Labour winners, for instance. I'm creating my own prediction data. then you can also use that, right? To predict with new data given the model. So it's a simple prediction. So I do this well. I'm just showing you another way of doing this here, so don't get confused. So I mean, you can always use these tag functions, libraries. It makes our lives easier. But if you don't trust them, create them yourself. But sometimes there's no need to reinvent the wheel, so it's up to you. But in either case, what I'm going to do is I have 4 models, and I'm going to make 4 predictions. But I'll do it first. But so this is actually this scattered plot. So this is the margin. So it's slope, and this is ln wealth. All right. Log net wealth. All right. So these are regression, and then I add regression lines. So you already see. So this is for labor. Yes, this is for labor. There's a little jump. Whether that's statistically significant or not, we don't know it yet. But there's a jump, right? So this jump is actually the RDD estimate, all right? And so I'm just making this nicer. So this is so grid extra is just a library that allows you to put figures side by side. So here this is a plot for labor, and this is for Tori. And look, for Tories, for conservatives, there's a jump just at the threshold. So, and this says something, right? So this says, and by the way, here I'm using the whole sample. So I'm not focusing on I'm not focusing on a window. That's like a whole another story. But if you just do predictions at the margin, that difference is RDD here. So so this is visually I'm showing this, but you can also calculate it, right? So I'm just at the margin 0, I'm just looking at predictions. So spread predictions is just allows you to do predictions in multiple models. And again, another convenient function, but you don't have to you don't have to use this. So this is the difference for Tories. So this is in log terms, but there seems to be a difference, right? And this difference, since this is in log terms, if you just exponentiate it, right? Since it's log, so if you exponentiate it, it's going to give you in pounds. The difference actually, so the difference between these two things is 200,000, like it's 250,000 pounds. And this is a big number, right? And if you look at the average wealth in the data, it's also around 250,000. Which means conservative MPs doubles their wealth when they become a member of a party. So, and this is only for conservatives. If you look at labor, they don't have that result. And the authors argue that this is because conservatives have more connections with private sector. So once they stop being an MP, they just go and take these lucrative, wealthy businesses. They do consulting, they just give talks here and there, they get their monies. While labor MPs, well, they are labor MPs. So it's they don't have those connections. So that's if you read the paper, that's the argument.
Any comments about the slope after the tree? Because for the Tories, it's kind of like flat.
Yeah.
And then for the
that's not what they do, by the way. They I want to start with like very simple, and this is what Imai does in the textbook as well. But I'll come to that. I mean, this is whether this is a good fit or not is a problem. Well, again, 2 problems, right? We are actually covering this at the margin, but I'm using all sample. So all these losers who lost by 50% are also in the sample, who are also determining the slope of this line. Well, they probably shouldn't, right? So again, as I told you, RDD literature, the methodological papers focus on these 2 things: how to determine the window size and also what to fit. You can also, instead of a linear, you can also fit more flexible local polynomial-like styles. So just a little bit of notation. So this is what we wanna estimate. So conditional sum covariates. So I'm approaching the outcome from left and from the right, and they just jump at the threshold, right? So if you just look at the outcomes, well, this is what we did here, right? I'm just just look at here at the margin, and then look at here, just compute the difference. So if you in formal notation, it's gonna be it's the limit from the left and from the right. Correct? So, but the problem is Onur Hocam mentioned. So I mean there are problems, right? I'm using here, for instance, all these data points which I shouldn't be using. So then what to do? So I'm not going to go into details, but so there is this trade-off right here. So if you can use, and also like in terms of what you did. So here we fitted a linear line, but there's no, there's nothing that stops up. You can use also more flexible parametric approaches, right? You can also fit a more a flexible line. So, but there are trade-offs like on what you did. So if you go and read RDT papers, most of the time they will show you results with different specifications. So I think it matters, especially for instance, there are all these data-driven window sizes, which essentially uses a trade-off between bias and variance, right? If you go, so what's the trade-off here? So let's say I'm focusing on a very narrow, let's say 1%, like 1% to the left, 1% to the right. So that's a very narrow window, which is nice for bias, right? Because they're going to be super compatible. Because they barely lost, like they lost with 1% difference, less than 1%. But what's going to be caused? We will have very few observations, right? So when you have very few observations, of course, that's going to be problematic because you cannot make there will be a lot of uncertainty because data points are going to be scarce. Then if you want to have more data points, well, then you're going to be far away from the cutoff, which would introduce some bias. So that's the trade-off between bias and variance, which of course these bandwidths, they are called, the window sizes. So there are all these, there is one Invents and Indian guy, that's hard to pronounce last name, Kalyaranamaran. Yes. No, I'm not, it's a hard Indian last name. So IK bandwidth, for instance, uses that logic, the trade-off between bias and variance. And there is also Canonico et al. So they also have this non-parametric approach. I mean, this is also quite a math-heavy methods paper. But what they do is, so there is this window problem. But there is also another problem. So if, for instance, here I did a parametric approach, right? I used fitted like a linear line. But you could also have non-parametric approach. The problem is when you have all these non-parametric approaches. So, for instance, local linear regression, something like local linear. It is also, but it also has a problem at the boundaries. Well, I actually had one picture, but so go and check the paper. The problem is since they are so flexible, like all these local polynomials, they perform poorly at the boundary, meaning that when you approach that boundary, for instance, even a little like 1 point can just bring a lot of changes because they are flexible approach. Let's say it's kind of the outlier problem we discussed before. So this is the cutoff. Let's say margin is 0. Then you have some points here, and then let's say some points here, and then there is one here, like a very clear one data point. Since these are, you can't just fit local, very flexible, high degree polynomial. Since they are flexible, it's gonna just fit, and then this is gonna be something like this, right? And then if you just estimate the RDD, the difference is gonna be huge, but that's gonna be driven by this one data point. So that's why this Canonico et al, they also incorporate that bias. So they fix that bias as well. So, state of the art right now in RDD, use their method. That's the model of the story. And they also have a nice package. I mean, I'm not going to show you here, but you can, for instance, simply, what I, for instance, normally use to show in my class is take this data and use their method. And that's going to be a good practice for you. And you can also see how it's all right. Any question about RDD? How are you doing on time? Okay, so questions, comments? So sorry, I mean, our RDD part was a bit, but hopefully it gave you the idea, right? So there needs to be a like a discontinuous jump, where treatment, like there will be, you know, there will be a switch. So, you know, there will be like a treatment assignment. The example was being a member of parliament. It's hard to find such discontinuities, right? But now that you know, if, for instance, there are all these financial thresholds, like for instance, Duke, that's where I got my PhD, recently announced so now they are giving full scholarship to Carolina residents if their family income is below 150,000 US dollars. Oh, one thing that I didn't mention, of course, is so if there is manipulation around the cutoff, you cannot use RDD, right? If you can manipulate perfectly in a way that you just switch from, from being left to the right, then of course, so that's the identification assumption of RDD. So let's say, you cannot just manipulate your income in the US, let's assume. Then that's a nice RDD design, right? You can just look at the value of Duke education, right? On students whose family income is just, we can compare students who are, who went to Duke because of the scholarship and who barely, lost the scholarship and couldn't go to Duke, like those who are going to be, oh, sorry, that's going to be based on income. Never mind. So, well, still, yeah. So those who are above, let's say, will be not eligible for, will not be eligible for scholarship, and some of them are not going to go to Duke, right? So, and those below, they're going to be eligible and they're going to go to Duke. So you can first compare them. So they're going to be comparable in terms of all characteristics, right? Technical characteristics and everything. But that's only the case if you just focus on this narrow threshold around that 150,000 US dollars. And again, going back to identification assumption, you cannot, I mean, if there's manipulation around the cutoff, which I showed you there was one figure from one of our papers again. So for instance, in Turkey, again, going back to that public procurement data, what we do, for instance, there are also thresholds in the law. If it is above a certain Turkish lira, you cannot use methods that are less transparent. You have to use sealed auction bid method, which is the most transparent one, if it is above a certain threshold. But what happens is that procuring agencies in Turkey, they manipulate it, right? So they manipulate in a way that, they stay below the threshold so that they use all these less transparent methods. And if you just look at the density, distribution, you see these hump, like there's like a sudden jump just before the cutoff, which shows actually one test for RDD, whether there is a manipulation around cutoff or not, is simply looking at the distribution of the running variable. Running variable is essentially it's the variable around which there's like a threshold, like there's a threshold for this. In this case, it's what the running variable. So you can simply look at the distribution, and if there is a jump, like there's just increase just below the threshold, that means they are manipulating the threshold. So in order for a valid RDD design, there needs to be no manipulation around the cutoff, and that it's like parallel transassumption, correct? So that needs to be tested. Okay, so I'll just show you. Well, this is you're gonna do it when you're back, right? So I wanted to something simple, like canonical design. And I also wanted to have some sort of a media data. Unfortunately, it's not social media data. So, question is: do elections increase bias coverage towards opposition in competitive authoritarianisms like ours? So, what I did was I just scraped Sabah newspaper. Right, this is one pro-government newspaper, and here the outcome is negative sentiment towards opposition newspaper articles. And I want you to answer this question with a simple DID, like a canonical design. All right. And treatment in this case would be, opposition articles. And election, I also had to make a decision there. Official announcement of elections was March. Well, it's a bit messy, but let me show you. So I also show you how to scrape the data and, how to prepare. This is in Python. And just a simple, like, you can collect, you can just iterate over the sitemaps, collect everything that Sabah published. Once you have that, you can parse them again, and I assume you already learned some Python already. Beautiful Soup is the library that you might want to use, but you can also do this in R. So once you have the URLs, because I collected it here, but I already did this for you, but in case you are wondering, then just parse the title, main text, and then the date when the story is published. I only filtered the articles that are about AKP, Erdogan, Kılıçdaroğlu, and CHP. So position party and government party. Then of course negative sentiment like this. The outcome is here negative attitudes, like negative sentiment towards the opposition. Here I'm just using already a fine-tuned model. I think you already saw some Word presentations yesterday. So this is already fine-tuned, which is like that. But it's fine-tuned using like movie reviews. Like I think there's also like a couple of data sets. They're all about product reviews. So which is not a good model. So our measure, our measure is our measure is a bit messy. And I just using this model, I just labeled the titles. All right. So I mean, it's not the perfect measure, but it works. So anyway, so what you have in the end is okay, this is the answer. So you have just this around 3,000 newspaper articles. Some of them are about the, some of them are about the government party, and then we have this election period. So who? So that's community design. Well, you have you have the answers, and you can always ask about the application. Just do it, and well, you won't find anything. That's the spoiler for you, but yeah, that would be a nice practice, I guess. All right, any questions?
These slides with us.
Yeah. So yeah, I'll send you the PDF version maybe. Since this is HTML, PDF.
One, they're extremely valuable. Two, they may not have.
Yeah. I'll send you, but I'll send you a Jam and Jam is gonna. Any questions? Comments? But hopefully that was well, it was a bit quick, but yes.
Can we use this discrete data?
What do you mean by discrete in terms of outcome variable or? So for instance, it's well, in this case, for instance, it is actually discrete. It's either 0 or 1, for instance. 1 if it is negative, 0 if it is not. And I simply use OLS. It's fine. I mean, well, one could argue you could also use budget, but it's fine. As long as one problem, like using OLS in binary variable is like you can have out of you can have predictions like larger than 1 or smaller than 0. But if you just do predictions and if they are within the range, totally fine to use OLS as well. But the values in like the outcome, like it can be count variable. Like this is like the things I showed you. They are about designs, and you can always use other type like logistic regression, Poisson regression if it is count variable, right? So and for instance, like for RDD, it's just well, in RDD, it could, I'm thinking now, let's say you have discrete Y's, again, still it's going to be fine. It's just, I think you need to be more careful about how we fit. But but these are like design, like the ID and RDD, it's about design. And how we're going to estimate the model is like because like for Calavay and Santana, it's not even regression, right? It's a angle. So, depending on the outcome, you might have.
There are even different things that will best for matching.
Yeah, exactly. I mean, these are just two designs. Like for instance, you could also have matching as well. That's the problem with matching. Of course, it's like the same problem we have like for like on what things you're gonna match on, right? It's like statistical controls, like what type of controls you're gonna have, and what kind of covariance you're gonna match on. There's a nice meme on Twitter if you go. It was a chart like the current British king. What was it called? Charles and Marilyn Monroe, if you match on age, like nationality and a couple of things, they are gonna be matched. So that's stuff like that. It's I just Google it, you'll find it. So that's a problem for this matching like on what covariance is gonna match. But yeah, the IB and RBD, yeah, they're gonna if identifying assumptions are satisfied, it's gonna allow you to have that causal score. But so parallel trends in the IB and no manipulation around the cutoff for RBD. All right. You have a question? If not, I guess you have a bus to catch.
Yes, please join me in.